All right, welcome. This is the first of a five-part series that we're doing over the next 3 days. Most of you will probably only be watching 2 or 3 of the topics, but there are 5 parts if you're interested. As mentioned, it's been recorded, and all 5 will be recorded and available to you free of charge. I'm Ryan Holger with Temperature Equipment Corporation. You may not know who we are. Maybe you do know who we are. We're a local HVAC distributor that's been around since 1935. And we do a lot of carrier equipment as well as many other manufacturers, some 60-some manufacturers that we deal with. But those of you that work in schools and restaurants and fitness centers and stuff like that probably have no idea who we are because we're behind the scenes. But today we're trying to give you some information out there. This is not meant to be some sort of sales pitch or anything like that. And those of you that know me know that that's not my thing. I want to educate you and then have you make your own choices on whatever stuff you need. So a lot of what we're talking about today is brand agnostic, generic type information. I'm going to check the question box every once in a while, but I'm going to minimize it now just so it's a little bit easier for me to see everything on the screen. All right, so as mentioned, this is a 5-part series. Tomorrow morning at 10 o'clock, there is a version of this that is specific to restaurants. In the afternoon, there's one for indoor sports, which would be fitness centers, basketball gyms, martial arts rooms, wrestling rooms, cycling centers, anything like that. And then there's a section on Friday morning for schools, specifically K through 12. And then following up Friday afternoon with ideas for your own house, right? You're trying to fix your business, obviously, and then what can you do at your own house to make things better as well. If you register for one, you're registered for all. So the exact same link you logged in with today, you'll use that exact same link again tomorrow at 10 a.m. if you're interested. So our agenda for today, we're going to talk about indoor air quality pollutants. We're going to talk about filtration as a solution to those pollutants, fresh air as a solution, UVC lights, and then some of the other stuff that's out there as well. We'll kind of touch on a lot of things today. This is meant to be sort of a broad overview, introduction, and then more fine detail on those other 4 dates. So if you didn't know, the pollutants that are in the air typically get lumped into 3 buckets. There's particulates, microbials, and gases. Particulates are physical chunks of things, right? So most particulates that we see visually floating around the air, that's dust. And if you didn't know, dust is primarily human skin cells. There's dander, which is stuff flaking off of your pets at home or if you run a pet shop or something like that. And then there's pollen, which is stuff coming off the plants. Those 3 things are the vast majority of the particulates that we deal with in the indoor environment. There can be other stuff as well. You could live next to some kind of a coal-fired power plant. There could be particulates floating into your air that way into your building. But these are the main things that would be particulates. Microbials, and that's of specific interest to us today, because as you probably know, this 5-part series is going to have a heavy focus on COVID-related stuff. So microbials get 3 buckets as well. There's bacteria. Now, there can be good bacteria, like the bacteria in your stomach that breaks down food. We're not so concerned with that for this discussion. We're talking about the bad bacteria and specifically bacteria that's in the air and in surfaces in your occupied spaces. So things like strep throat or E. coli or something like that. Then we have viruses, which traditionally we're mostly concerned with influenza as well as the common cold. But sometimes, and this is one of those sometimes, we're concerned with other more exotic things. In this case, the SARS-CoV-2 virus, which isn't even on my old slide here, by the way. I have the old SARS listed on there, right? Or H1N1 or the norovirus or something like that that's taken over and becoming an issue. But we're going to lump all those viruses into a discussion, and then we'll also have a specific focus on COVID, obviously. And then we have mold spores, fungus type stuff. And then mold, obviously there's good mold and bad mold. Mold on your orange makes penicillin, right? Everyone's heard that story. So that's not the bad mold we're talking about, or blue cheese can be mold, right? But we're talking about the bad stuff, something that's growing in your wall, on your flooring, something like that we want to deal with. The third category of stuff that's bad to have in the space are the gases. And there's 2 specific categories of gases that we're primarily concerned with in indoor buildings. One is VOCs, volatile organic compounds. So this is the off-gassing of numerous materials that you put into your building, furnishings, desks, the kind of paint that you use, the sealants that you use, whatever, cleaning chemicals, those kind of things. And some people will have reactions and headaches and stuff like that because of it, and we want to get rid of those. And then we have odors. Odors are things that are not harmful necessarily, but you just don't want to smell them. Like, so if the dude next to me in the next cubicle has some kind of weird cologne and I don't like it, I don't really want to smell that, right? So things like that could come up that we want to get rid of as well. So the methods to getting rid of some of this stuff. Looks like a question popped up. Let me pull that up real quick. Paul asks if these are available on demand later. Yes, they will be later on this evening. This one will be posted, and the same thing with the next 2 evenings as well. Filtration is one way to get stuff out of the air. This is the primary way that we deal with particulates. There's all kinds of levels of filtration, so just having a filter on a piece of equipment is probably not enough. The main purpose of having filters on HVAC, heating, venting, and air conditioning equipment, the main purpose of those filters is to keep those pieces of equipment clean, and so they can do a good job exchanging heat. It isn't really for your health purposes. If you want to do filtration for health purposes, you really got to beef things up, right? A little bit better. So in order for us to decide what we need to be able to deal with from a filtration standpoint, I need to know what you want to catch. What do you want to get out of the air? What you want to get out of the air is going to have all my answers in it. So I need to know how big the things are that you want to catch. We measure small things on a scale called microns, which is kind of a nickname for micrometers. So we measure on microns. So if I look at something like hair, it's over here in the 60, 70, 80 micron range. But if I want to deal with something smaller like bacteria, viruses are very small. Gases and odors are super small, right? They're basically the same size as my air, obviously, because gas and air is gas. So those things are much harder to deal with. The smaller something is, the harder it's going to be to capture. So as you might expect, it's significantly easier for me to catch pollen out of the air than it is to catch virus out of the air. But we can do it. So how small is this stuff? On the left is a piece of sand, 90 micrometers. Human hair, PM10. So if you haven't heard, PM10 and PM2.5 are two commonly measured sizes of particles. And even sometimes like your weather app on your phone will say that it'll list the PM10 and PM2.5 for outdoor conditions for that particular day, and you can decide if you should be outside that day or not. I would argue that your indoor air is probably worse, so you might as well hang out outside, right? But those are two really common measurement points, and that shows you how small they are, the blue dot and the red dot. And if I want to look and try to deal with the SARS-CoV-2, it's 0.12 microns. So it's that little tiny dot inside the blue box. That's how small this stuff is that we want to get compared to a giant piece of sand over here, right? And sand is pretty small. So this is super small type stuff. Another way to look at it, here's PM10 on the right. PM2.5 is this black one here. There's your red blood cell. So PM2.5 is smaller than a red blood cell. Bacteria is even smaller than that. And then over here is your COVID, but it's not this guy. It's the little tiny dot right there. We're just showing it as a blown up version. That's how small this thing is. Way, way smaller than a blood cell. Way, way smaller than bacteria. It's really tiny. However, the good news is that the SARS-CoV-2 virus is significantly larger than most viruses. It's a big virus, right, as opposed to a little virus. A lot of these viruses are super tiny. This one's on the big scale, 0.11, 0.12, 0.13 type range. He's over here. So this virus is so big, he's about as big as a small bacteria. So I got a little bit better chance at catching him than I would a different virus. What ways can we filter stuff out of the air? We have three main mechanisms we can use for filtration: mechanical filtration, electrostatic or electronic filtration, and chemical gas phase filtration. We're going to focus on mechanical filtration because that's by far commercial buildings. 99% of the buildings are going to have something like that. The chemical stuff is for industrial processes. That's a whole different category. The electronic stuff has its own issues, meaning that you have to constantly clean these plates, which is not a problem. I mean, you can clean them and they'll do a good job catching more stuff. But once they got stuff on them, that's it. They don't do anything. Most people would rather have the disposable type. They throw it away, they put a new one in. So we're going to focus a little more on mechanical filtration, at least for right now. So your mechanical filter, the really crappy one you have in your system now, or a really good one that you may have just put in for trying to catch small stuff, it uses 4 different mechanisms to catch things. These are my 4 mechanisms. The first one is impingement. So on these little drawings, this blue circle is one little fiber inside my filter. So if I look at my filter, it's one little piece of fiberglass in here, right? Or any of these other types of media that I have. It's one little piece of it. In this case, my piece of particulate that I'm trying to catch is dust for this example. And these lines represent my airflow coming through the system. So here's my filter, here's my airflow coming through. Impingement means my debris, my dust in this case, has a head-on collision with the fiber, with the brick wall, slams right into the wall, and there he is. He's just sitting there, and that's it. We caught him. That's impingement. That one's easy to understand. Interception, not too bad to understand either. I did not have a head-on collision. I had a glancing blow, and as I slid across this fiber, it created friction, which slowed me down. Very much like if you were getting on the interstate and you got a little out of control and you hit that guardrail and you start grinding your car along the side of the guardrail, it's going to start slowing your car down. It's like that, right? Hopefully no one's done that recently. Then there's straining. This is the most obvious one. I have a hole that is this big. I have a piece of debris that is that big. It is obviously not going to fit through the hole. It's going to come up to the hole and just clog it, and then that is that. It's very much like when you boil pasta. You dump the water and pasta through the strainer. The water is small, so it fits through the hole. The pasta is big. It does not fit through the hole. So that's what happens in this case. But just like with a pasta bowl, if you ever dump pasta in the strainer, what do you always do afterwards? You always kind of move it around and kind of flip the pasta so the rest of the water can get through, because the initial pasta kind of clogged the holes up, and now I got a little bit of puddle of water in there. I got to shift stuff around to get it to go through. Well, the same thing's going to happen with the filter. If I have a small gap, the dust comes up, or whatever my debris is comes up, it fills the gap. Great, I caught him, good job. But now no more airflow can fit through there. So now the airflow's got to go another way. And as I clog more of those gaps, less and less airflow can get through there. And if I don't get enough airflow through my filter, it's going to cause issues with my heating and cooling system, even being able to operate. I don't know if you ever had a really dirty filter and it causes your furnace at home to hit a high limit switch because you don't have enough airflow and you got to put a new filter in. That kind of stuff will happen. The good news is, once I catch this piece of dirt, debris, dust, whatever it is, it's easier to catch more stuff. He's clogged the hole, so anybody coming along behind him keeps slamming into him, and they keep clogging it up more and more. So the dirtier the filter gets, the better job it is at catching stuff. Great, let's all have dirty filters. But remember the airflow side. I have to have the airflow, or I'm not going to get any heating and cooling, which kind of defeats the purpose of even having the system to begin with. So the filter is going to get dirtier and dirtier. It's going to catch more and more stuff. And at some point, it's going to get to the point where I say, it's time to change it because I can't get enough airflow anymore. The fourth mechanism used in mechanical filters to catch debris is called diffusion. This one's a little bit harder to understand, and I'd love to skip it and just move on. But if I don't explain it here on the filters, it's going to be really hard to understand some other stuff we're going to talk about later on here this afternoon. So in this case, you'll notice that I switched. I don't have dust as my particulate. I have something really small, way smaller than dust. I have a virus in this case. And you'll also notice that I don't have it all moving in a straight line. Now I'm showing it moving in this crazy zigzaggy line. That's because really small things don't move around in the airflow in the predictable ways that large things like dust would do. So what do I mean by that? So there's two things that normally move stuff around your building or your house. One is gravity. So if I have debris in the air, assuming I don't keep stirring things up, the debris in the air is probably slightly less weight than the air itself. So it'll slowly start falling down and it'll settle on counters and surfaces and floors, which is why you get dust on your counter and you got to wipe it up every once in a while. So things will fall out of the air and land on flat surfaces, and we can clean them up, vacuum them, sweep them, mop them, whatever I got to do. The other thing that happens is that the airflow through the room moves things around the room. So if I have a fan system bringing air into a room and bringing air back out of a room, if I have a piece of debris here, the airflow is going to come along and he's going to smack him and move him along, almost like the sail on a boat pushing him along. Well, here's what happens with really small stuff like a virus. The gravity pulling down on stuff, if you didn't know it, the earth is pulling you down to the earth, and your body's actually pulling the earth back up. It's just that you have such little mass that you don't got much shot at moving the earth, right? But objects all over the universe are pulling towards each other. They're pulling towards each other, and the more mass they have, the more they can pull. And because you have very little mass and the earth has a lot, you go towards him. When I get to the point of having a really small virus, the mass is almost zero. It's very close to zero. So there's nothing really for the earth to pull down in terms of gravity. I mean, it's pulling down, but not very much. I have the same problem, which means the viruses don't settle on the counter and I vacuum them up and wipe them up. I have the same problem with airflow. I got that sail and I got the wind coming along pushing the sail. Well, if you take your sails down and you just have a mast there on your boat, well, the wind isn't going to do very much. Is it going to push the mast? Yeah. Is it going to move the boat very much? Not really. Put the sail back up and away we go. So a virus is super tiny. So the wind, the airflow, mostly just goes right around it and only a little bit hits him. So because of that, really small particles, like viruses, don't really give a crap about gravity or airflow. They still move around, and they move around a lot, but they're moving around based on Brownian motion. What the hell is Brownian motion? All the really small stuff in the universe bounces off of other small stuff. It collides into somebody, and they both go shooting off in different directions. Then it collides into somebody else. And that's what we're showing here with the red line. He bounced off something, and then something else, and something hit somebody else, and somebody else hit him. And then maybe he went back this way, and then back this way. And eventually he might get his way over to this fiber, where once he gets super close to the fiber of my filter, that gravitational style force of two things attracting each other, when they're closer, it's stronger. So they'll be able to cling on to each other. And he'll just kind of hang out there by the filter at that point. So hopefully that makes sense, and it's going to make some stuff clear later on. Do we have any questions that came in while I was blabbering? We're not. No, we're good. So we'll move on. All right. When I'm going to select the filter for my system at my building, there are several factors that come into play. The efficiency of the filter. Can he catch the size of things that I want him to be able to catch? The pressure drop to the filter, meaning how restrictive is he going to be to moving airflow? I need to still move airflow through here. If not, there's no point in having a filter. I might as well have a concrete wall. Those are the biggest factors. And then there's the capacity of the filter and things like that. But how good am I at catching small stuff? And how much airflow am I accidentally going to block as a result of that? There's actually a test for this. There's an old test, ASHRAE 52.1. Ignore that. It's super old. ASHRAE 52.2 is the current test, or many of you may have heard of that as the MERV rating. When you buy a filter, if you buy a decent filter, it'll say a MERV rating on the side. If you buy a really low-end one, it won't say anything, which means it basically has a MERV rating of like 2 or 3, and it's useless. So it should have a MERV rating on there, which means the manufacturer of the filter had it tested professionally to a specific standard. Not that you guys necessarily care how the test works, but I'll give you the quickie version. What they do is this is your filter over here as the filter manufacturer. They stick it into this air handling stream. They bring air through here. They run it through a very awesome, super cool HEPA filter to get as much junk out of it as they can. Then they have an aerosol generator that intentionally makes particles and sprays them into the air. We have a particle counter that counts how many particles there are in the air. We run it through your filter, and then we count how many particles are left. So super clean air, inject stuff into the air on purpose of certain sizes, count how many we put in of those sizes, count how many you got rid of, right? And that's how we test these things. I say we, not me. I don't professionally test filters, but the testing labs do that. So this MERV scale, it goes from 1 to 20, 1 being the crappiest filter you could possibly find. I don't even know if, my t-shirt is probably like a MERV 1 or 2. So you have to really try to get a filter that bad. All the way to the high end, which is MERV 20. We kind of got these lumped in kind of like buckets of 4, if you will, to kind of illustrate to you the size of things that I'm likely to catch. Now, I don't know if anybody remembers the size of that virus we were talking about, COVID, 0.1, 0.12, something like that. So he's down in this range over here. If you have standard filters in your HVAC equipment, standard meaning you probably got a MERV 6 or a MERV 8 down over here, you are not catching a virus. You are probably not even catching bacteria. You're pretty much only catching big pieces of dust at that point. You need to get something that can catch much smaller stuff. Specifically, if you follow ASHRAE standards, and if you don't know who ASHRAE is, American Society of Heating, Refrigeration, and Air Conditioning Engineers, which is exactly why we just say ASHRAE. The recommendation from ASHRAE is that for buildings, and this has been going on since May, they had this recommendation, for buildings that want to have a shot at catching a good portion of the SARS-CoV-2 virus in the air, they need to put in MERV 14 filtration. And it's kind of weird because the recommendation then says, if your system can't handle the pressure drop penalty of a MERV 14 filter, at least go ahead and put a MERV 13 in. I don't understand what that means. Maybe they're recommending 13.5. I'm not sure exactly how that works. But the recommendation officially is MERV 14. And if you can't do 14, at least get 13. And you'll see why later on why that's at least better than nothing. But if you're going to do something like a MERV 10 or a MERV 8, forget about it. You're not catching any viruses. Zero. Absolutely zero. If you want to do better than a MERV 14, that's okay. A MERV 15 is a pretty achievable filtration rate. And then to go above MERV 15, you're up in the land of HEPA, which is fantastic filtration, but it's a very expensive filter. And more importantly, it requires me to put a much more powerful fan system into the building to be able to move the air through the HEPA. Doesn't mean you shouldn't do it, and you absolutely should think about it. And in some of the applications we do, like when we do hospital works and work in surgical suites, there's always HEPA in there, as well as other filtration technologies. But for most of the buildings you guys have, which are schools, restaurants, stuff like that, gymnasiums, you're probably not going to put a HEPA filter in. You might, but you're probably not. So the types of filters, we'll only look at a couple of these because a lot of these are pretty nichey. But for the type of equipment that most of you have, here's your low-end cheap panel filters. So if you have filters that look like this, you're not doing anything. I mean, you're doing something. You're catching stuff over here in this range. So you're catching like big pieces of dust. That's about it. I'm not doing anything for bacteria or viruses or anything like that. One of the things that we do is we put filters into this V-bank arrangement. Instead of having a straight line like you have at your furnace at home, your equipment in your building, your commercial building, we put them in a V-bank shape. And the reason for that is to get more surface area so I can slow the airflow down temporarily and catch more stuff. Sometimes you don't have space to do that. Like in a residential application, we don't have the space. Or in some small packaged rooftops that you might have on top of your restaurant, we don't have the space. So in some of those applications, we'll put in pleated filters. So instead of these kind of filters put into a V-bank arrangement, we'll put pleated filters in, which has little tiny V's all the way folded in there. So up, down, up, down, up, down, up, down. They're all folded in. So I have that same kind of effect where I have a lot of surface area, but I'm doing it in a small distance. And then if you're savvy, you'll take a pleated filter like this and then put it into a V-bank rack anyway. And now you can really slow down the airflow and catch a lot of stuff. We also have ones that have what I'm going to call mini pleats. So instead of these larger pleats, where I'm going to make up a number here, 20 pleats on this dimension, I might have 50 pleats going along. Many more folds, much more surface area, and I can get to higher and higher MERV rates by doing that. So the density of the material and the amount of surface area of the material I have will play a factor in getting me the higher MERV rating. It's going to be really hard to get above a MERV 12 with a normal filter, a normal everyday filter that you would just swap out. There are filters that'll do it. Some of you may have air handlers that can handle something like this. This is a bag filter. So think of this like as a 3-foot long grocery bag here, right? And all the airflow can go in there and then go out both sides of the bag. And another bag, another bag, another bag, another bag. It does a lot of surface area. I can catch a lot of stuff with that. I can also go to pretty dense media. Typically those will come in metal cartridges. And I can stick those into your airstream and shove all the air through there and get to MERV 13, 14, 15, 16, or even higher, MERV 17 and up, which would be HEPA. So MERV 17, 18, 19 is the HEPA range of filters. That means they're getting 99.97% of the fairly small 0.3 particle size things. 0.3 is still, or is still larger than COVID, which is 0.12, but I'm getting 99% of the 0.3, so I'm probably getting a decent amount of the 0.1 stuff. Not all of it, but a decent amount. We'll show you some stats on that as well. When I put these things into the filters, I have to do a good job. I can't have giant gaps between them, so I got to slide them all in and make sure they're compressed onto each other. And then when I shut the door to the cabinet, there's usually going to be a gasket type assembly on here. So those gaskets line up with the filter to compress it tighter. I don't want to have any air gaps for air to skip or bypass the filter, because air is going to take the path of least resistance. And if there's an air gap around it, I'm just going to send a lot of air that way and less will go through the filter. When I want to do higher levels of filtration, it's harder to shove air through that filter media. So that means more air is going to try to squeeze through the gaps. So I really got to do a good job of getting rid of the gaps. One of the best ways to do that is to caulk in between the filters. If I have these metal frame, these are bag style filters, but HEPA would be the same kind of story. I want to caulk in between those so that way I have one continuous wall of filters as opposed to wall, gap, wall, gap, wall, gap. If you don't have the ability to put HEPA filtration into your mechanical equipment, meaning your rooftop unit or your air handler or whatever you have, there are portable filtration options. There really wasn't too many of them until recently. I mean, there's like the tabletop one that you can get at like Best Buy or whatever, like that you might put in your house, but it's only going to be doing 80, 100, 150 CFM. That's not going to be anywhere near what you need for a place of business. So this is one option that we use a lot. And by use a lot, I mean the past 6 months. Prior to that, it was as a, just kind of a wish list item. But now it's a high volume type everyday thing that's going on. And essentially what you have in here is you have a blower assembly, very similar to the blower assembly you have at your furnace at your house that can move a decent amount of air. You have a HEPA filter in there, and then you have a pre-filter in front of the HEPA filter. That way the HEPA filter doesn't have to be changed as often. I want that HEPA filter to last 2, 3, 4 years because they're fairly expensive. And to do that, I'm going to put a inexpensive pre-filter on there that's kind of like a sacrificial lamb. Let him catch the big stuff, and I'll throw him away every couple months, and I'll put a new one in and let the HEPA keep doing its thing without swapping him out very often. This one here is a 600 CFM version. He's got a little brother that does 500. He's got a big brother that does 1,000. But you can move quite a bit of airflow. So these originally, we were putting them into hospital applications back in April, May timeframe. A lot of these areas of the hospital were getting repurposed for stuff, and this was one of the solutions to that. But since then, later on this summer, we started putting these in applications in schools. A lot of schools have difficulty getting good filtration. We'll explain that in detail in one of the other sessions, but this is a possible solution for that. And you can use it as a portable solution on wheels for just about any building type that you really want to. So there are ways to get it done if your air handling system built into your building cannot do it. So those really small things we're talking about, even when I'm talking about HEPA, I'm only going to be catching certain size particles. And I want to get down to the really, really small stuff. So when I get to really, really small stuff, it's about the size of air, maybe slightly bigger. Well, I can't put a filtration system in that catches all of the air because that's going to be a problem. So I have to have other ways to get rid of some of this really small stuff. There are several other ways we can do it. One of those technologies that we've been using a lot is from a company called Secure Air. Once again, I'm not pitching you a specific brand or technology. These guys just have really cool stuff. In fact, some of the guys that worked on this technology also developed some residential stuff back in the day. And I actually have one of the residential ones. It's a different brand that they built, but I have one of the residential ones at my house, and it works fantastic. In any case, we started using these guys back in 2013, specifically for hospital applications where we wanted to get really good filtration, but we didn't want to pay for all the energy to force air through really dense filters. That's where this kind of thing came into play. But now because of COVID, it's coming in significantly more often. So the idea here is that we want to be able to catch some of this really small particle stuff. And we have a lot of debris in the air, and we can measure that stuff. And I said 2.5 and 10 microns are common measurement points. But the really tiny stuff is in very large quantities. It is all over the place. And it's flying around, bouncing off of stuff. It doesn't care about airflow. It doesn't care about gravity. It doesn't get stuck in a filter. If it does find its way to a filter, it goes right through. It's really, really tiny. It's basically the same size as air. So when I get to the really tiny stuff, we're going to do something different with that. And I've already kind of showed you a lot of the tiny stuff before, but I'll give you a couple more examples of some of the bad things you might find in air that is smaller than 0.1 microns, which means it's really, really, really tiny stuff. Sorry, smaller than 1 micron, which means it's really tiny stuff. So how are we going to catch some of this stuff, right? Influenza, 0.09 microns. It's even smaller than COVID. The cold virus is even smaller than him. Some of these things are really, really tiny, right? So I got to find a different way. This technology is one of the different ways to do it. I'll show you 4 or 5 different things that we can do. This is one of those things. When I say we, the whole HVAC industry can do this stuff. It's not something that you would just like order in the catalog or whatever. This is usually designed for your building because it's got to fit in whatever kind of HVAC equipment you already have. And there's all kinds of varieties of equipment, which is why we have the other breakout sessions for restaurants and schools and stuff like that as part of this course. So the airflow is going to come through here. It's going to go through a grid assembly that's going to condition the air. So there's going to be electrical power on this grid that's going to be charging things positively, right? You can charge positive, negative. So we're going to charge stuff positive and negative and get them to attract onto each other. I want them to be charged, conditioned, and then they're going to collide because positives and negatives are going to slam into each other because positive and negatives attract, right? If you don't believe me, listen to any song from the 1980s. Then what's going to happen is because now they've attracted, they are larger. They're not super small. They're just regular small. So now they're going to get stuck in the filter that is after that conditioning and collision assembly. So it gets stuck in the filter because it's bigger. Now, if it's not big enough to get stuck in the filter, that's okay because all the things that I charge that are still small are going to go right through the filter into the airstream and sort of kind of make their way back into the space. It'll be haphazard. They'll be bouncing all over the place with the Brownian motion, but eventually they're going to get back into the space. But now they either have a positive or negative charge. And as they're traveling down the duct system and back into your space, the positive and negatives are attracting, and I'm making these larger clumps of stuff. Well, now that I made larger clumps of stuff, which may include the germs that are in your space, they're larger, and now all of a sudden they do care about gravity, and they do settle on the counter where I can wipe them up with a Clorox wipe, or they do fall on the floor where I can mop them or vacuum them up, or they do get entrained into the airflow where they can suck their way back to the filter and get captured. So not only is this going to be pretty good filtration, but it's also going to help deal with stuff in the air, in the space, not just in the system. So in the actual building where you're occupying it, we want to find ways to attack the germs there, as opposed to passively waiting for the germ to make its way to my filter where I might catch it. This just kind of shows you a picture of it. It looks kind of like a regular filter assembly, but in front of the filter assembly, there's going to be a conditioner that charges these particles, and then it's going to go through the filter assembly. This guy gets a MERV 15 rating, which is pretty good. Remember, ASHRAE recommends we need for MERV 14 to have a shot at catching COVID. So MERV 15 is probably going to do it. But on the flip side, he has a really low pressure drop. 0.28 inches of pressure drop is very low for a filter that's MERV 15. That's the kind of filter drop that you would see on a normal like MERV 10 or MERV 12. So I'm going to get really good filtration without having to pay for the high cost of fan energy because of the pressure drop. So that's a pretty good combination of energy consumption versus capturing ability. Going to be able to capture and activate all kinds of things, viruses, bacteria, mold, at a pretty good clip, 99% for most of these things. All right, the last piece of this one, and we'll move on to the next technology, is that this filter, because I'm using electricity and filter media, and because it doesn't have a very large pressure drop, means I don't have to change it very often at all. So on this particular example, on this air handler that somebody had looked at, somebody smarter than me that had time to graph it all out, the pressure drop was building up on this guy, this MERV 15 secure air type filter, and eventually it gets to a point where it kind of spikes up at month, in this example, month 16, 17, something like that, and now I got to change it. Whereas a standard MERV 13, which is not even as good as the secure MERV 15, he builds up pressure pretty quick. I got to take them out and throw them away, put a new one in, builds up pressure over the next 4, 5, 6 months, throw them away, put a new one in. So I might be able to do less filter changes as well. I'll save electrical energy on my fan system, slightly less filter changes, although the filters are more expensive, so there's a trade-off there, and a much better job of filtering stuff. All right. This guy, though, if you saw on the one slide, he's like 9 inches thick, this whole assembly. That's not going to fit in a lot of your existing equipment. Yeah, if you got a hospital or something, we have big air handling systems, we'll make that fit. But on some little tiny thing at your restaurant, probably not going to happen. So we might look at other technologies that are similar, maybe not quite as good, but similar and more compact. So we look at these ones very often. These are 1 and 2 inch depth filters, which fit into your standard filter rack that you have on almost all of your existing equipment, but they also have an electrical connection to them as well. So they get a kind of a combination of that ionizing, that charging, and the actual filtration with the filter media. So you get kind of the combination of the two without having to have a very much pressure drop and without needing a special rack or space to put them in. So we'll dive into that more as we get into some of the other modules in the coming seminars. The next thing I want to talk about is getting some fresh air into the building. If you didn't know it, the indoor air that you are in is almost always significantly worse than the outdoor air. Now, there's times that's not true. You might be in a certain area where there's a lot of pollution, and Chicago is not even a lot of pollution as far as this discussion. Mexico City, a lot of pollution. Sometimes the outdoor air is worse than the indoor air there. But around here in the Midwest, where a lot of you are from, the outdoor air is almost always better than the indoor air, unless you're next to some kind of manufacturing thing that's spewing stuff in the air. So as people and things are happening in the building and pollutants are being generated, people are coughing, people have buy a new desk chair and it's giving off VOCs, whatever it is, I need to get rid of that stuff. And there's two ways that I'm going to get rid of that stuff. I'm going to exhaust air out of the building, and I'd like to do that where the problem is. So depending on my kind of application, I might need an exhaust fan over a fume hood, exhaust fan over a kitchen stove, exhaust fan in a bathroom. Try to have the exhaust be wherever the pollutant is that I don't want. Additionally, I need to have fresh outside air coming in. This is required by code, both commercially and residentially. Almost every space, it's required by code. So you need to bring fresh air into your building. If you're not doing that, you're doing a very big disservice to all of your occupants in the building, and you're also not in compliance with any local codes. So I got to bring fresh air into the building as well. And I usually want to supply that to all the occupied spaces, and then I'll exhaust it out through some main exhaust fan, or I might have a return system that brings air back to my air handling unit, and if there's a little bit too much of it, I can exhaust a little portion of that out. How much outside air should I bring in? There's historical tables you can look at to see what various codes have done over time. I am going to skip all that discussion and just show you what's probably required in your community. I say probably because it's not always the same. This is ASHRAE 62.1 ventilation requirements. This exact table is also in the International Mechanical Code, and that mechanical code is adopted by almost all jurisdictions. So almost every city or county, or in some cases a whole state, adopts this code, or at least the tables from this code. So this is pretty much code in most places. With that being said, the city of Chicago has its own table, and the state of Wisconsin has its own rates. But pretty much everywhere else I ever go, Chicago suburbs, Minnesota, Indiana, they're going to have this same exact table with these same numbers. So long story short, you got to look at the table for your code, but this is probably your table. This is one of like 5 or 6 pages though, right? And for right now, I'm just going to blow up the office building example. As we do other modules this week with you, we'll bring up other examples. But a typical office space, like you are probably sitting in right now, unless you're at home, which half of you are, you need to have 5 CFM for each person plus 0.06 CFM per square foot. So 2 things. First off, ignore the liters per second columns. That's for metric. We don't care about that. So we're using the CFM and the CFM columns. CFM is cubic feet per minute. So it's how, if I took a 1 by 1 by 1 box, how many boxes of that much outside air could I bring into your building per minute? So I need 5 CFM of those cubic volume of boxes for every person that's going to be in this space, and 0.06 times the square footage of the space. The per person part is to take care of the people pollutants. People come into a building, they have germs, they have cough, they have weird perfumes, whatever. I need to dilute their body odors and effluents down. And then the per square foot is because of the building. The building has pollutants. It's got some weird odor from the bathroom. It's got some chemical cleaner we used on the countertop. The paints we used were high VOC when we painted the wall 4 years ago. Whatever it is, I got to dilute that stuff down. So I'm going to add those 2 numbers together to figure out how much fresh air I need into my space. Now, there have been some recommendations from the CDC early on, and even ASHRAE back in May, saying, hey, you might want to think about over-ventilating your space. Over-ventilating, what does that mean? Well, that means not only get up to the code required amount of airflow that these tables tell you, but then why don't you do a little bit more, like really bring in a lot of fresh air for people? And that's okay if your system is designed to handle that, but it probably wasn't designed for that. Your heating and your cooling system was only designed for this amount. So if you bring in double that amount, for example, it's going to cause problems. Now, right now, today, it probably wouldn't be a problem at all. Your system could handle it, right? It's not that humid outside. It's not that cold outside. But in the middle of the summer, this is looking at a specific building, the indoor humidity was all in check until they made that change to follow the CDC and ASHRAE guidelines of bringing in more ventilation. And then all of a sudden, the indoor humidity was horrible. Well, yeah, you're sucking in a lot of moist air from outside all summer long. Yeah, it's going to be a problem. Your system can't handle that. So you want to get back up to the code required amount of air, the amount of air you should have always had all along. And then if you want to do more than that, you're going to have to do some calculations to see if your equipment can handle it, or someone's going to have to do the calculations for you to see if your equipment can handle it. And then you can decide, are we going to do it? Are we going to get new equipment? Are we going to keep our existing equipment and not do it? But at least get up to the code required amount. The humidity being out of line is a problem, and it's a problem for lots of things. There are certain viruses, bacteria, funguses that thrive when it's really dry, static electricity, door shocks, that kind of stuff. And then there's other things that thrive when it's moist, obviously fungus and mold being a big one. So I want to keep stuff in a tight range. This is the Stirling chart, also from ASHRAE, by the way, and it's been around forever, like 30 years. And the recommendation is to keep the humidity indoors between 30 and 60%. So if it's really dry in your space, find a way to get it up to 30%. If it's really humid, try to find a way to get it down to 60% to keep things in line, less bad things. If we look at more specific bad things, influenza, and obviously we're going into flu season right now, and this chart is a little bit challenging to handle. First off, let me put Fahrenheit on here because the British guy I got this from that did the study in Celsius doesn't like Fahrenheit. Surprise. So these are temperatures going across over here. These are relative humidity on the vertical axis. And then these curves are the risk factor associated with someone catching influenza in that environment. So red means you have no chance of catching influenza, 0. So if I heat your space up to 86 degrees, you're not going to get the flu. Well, nobody wants to sit in an 86-degree room, so that's a little bit ridiculous, but that would be the case. If I go down to 10% chance of influenza risk, right, I get little dips in here, more dips and more dips. So if I say like 50% chance, I'd have to keep your space at 77 degrees and below, say, 40% relative humidity. If it starts getting more humid, this guy dips down. Great. So I don't read these lines. That's not how you read this. You read across your temperature. So let's say I'm going to heat your building in the winter to 68. Pretty common heating set point, maybe 70, but 68 is already on there, so let's use that. So I have like an 85% chance if I have this low humidity. I have a pretty decent chance at getting something, all right? My risk factors can be fairly large. But once I get above like 45% to like 60%, as I'm reading across here, these lower risk curves start moving their way into my territory, my 68-degree line. And what went from an 80% chance goes to a 25% chance if I can get you to the exact middle here at 50%. If I can get you to 50% humidity, or let's say between 45 and 55, you're going to have a 25% chance at 68 degrees instead of an 80% chance. And if it gets too humid, the risks start going back up. So I want to be here where this divot is, 40 to 50, 40 to 60, 45 to 55, something like that. Coronaviruses, similar case. This one is not SARS-CoV-2 specifically because it's prior to the existence of this data. But most of the new data coming out now the past month has been similar. This is showing you how much of the virus stays viable for how many days at various humidities. So if I have a dry space at 20%, it's this black line, and it's going to stay viable for a really long time. I'll get down to, let's say, only 10% of the virus surviving after 2 weeks. That's assuming you're not generating new viruses. If I have relatively humid stuff, 80% humidity, which is really high in green, right? That's this line going down this way. I can get down to 10% survival rate of the virus in 5 days. If I want to get down to killing 99% of the virus off, it's going to take me like 10 days and so on. If I get to that middle range, 50% relative humidity, it's much sharper curve, right? After just 1 day, I'm already down to like 15% of the virus being left and 85% being gone. After 2 days, right, I'm over here with 99% of it being gone. So got to get that humidity into the middle range. I won't keep beating this dead horse, but you may want to, depending on the type of space you have, choose to add humidification to it, because every single study that we pull up and look at, here's another one in blue, 68-degree room, and these are humidities down here. If I get to 50%, I can do a pretty good job at eliminating most of the viruses in the space. But if it's too dry or too humid, bad things happen. And you probably all are aware the COVID rates have been going up lately, the metrics, and I don't know all the reasons because that's not my field of study, but I would not be surprised if somebody comes out later on and says, yeah, you know, it's because we're all inside buildings and the inside buildings are all dry. So viruses are surviving longer, so you're better chance of catching it. The exact same reason why we have the flu season when it's cold out and we stay indoors and we have dry conditions, and the flu virus survives longer in dry conditions. Same deal. There's also this calculator from the Department of Homeland Security. I don't know if you guys have seen this or not. You can adjust the UV index, the temperature, and the relative humidity and see how long COVID is going to be able to survive. So the way I have it adjusted right now with a UV of 4, temperature of 73, and a humidity of 46, 50% of it would be gone in 5 minutes. 99% is gone in a half an hour, right? So this is meant to be used to make those kind of determinations. But what you have to understand is in the middle of the winter, it may be hard to get your building up to 46%. So this number is going to be lower, right? Temperature is pretty easy to do what you want with. UV is much harder. This is not UV like a UV light bulb in your duct. This is UV from the sun shining on something continuously for hours at a time. That's what this is here, long shine durations. So this is for outdoor use. But if you want to bastardize it for indoor use, you can do that. But you got to take into account what the UV rates are. Even outside in Chicago, where I'm close to right now, this week I have a UV index of 2 at noon. This is 4. I have to go down to 2 just right now. Now in the summertime, it's a little bit higher, right? If I was in Miami, instead of 2, I might have 5 as my UV index. But when I'm indoors, it's going to be much lower. If I'm indoors at a window, okay, maybe that's a decent story. If the sun's shining through the window and shining directly in my area, okay. But if I'm in an interior space, the UV is 0. You got to move this guy all the way down to 0 or 1. So if I'm at a window, I'm probably at a UV index of only 1 because that window is buffering a lot of sunlight for me. So at a UV index of 1, keeping the other things the same, those numbers all basically tripled in terms of how long stuff survives. If I go to a completely interior zone where I don't sit in the direct sunlight, and put this UV index at 0, these numbers really go up. I went from 5 minutes, getting rid of half of it, to 15 minutes, to now I'm at 41 minutes, 270 minutes to get rid of all of it. So it's a pretty decent clip. So don't bank yourself on this UV sunlight saving the day unless you happen to work outdoors. But I can use this same scale to kind of make adjustments to humidity and temperature and see what happens there. So if I lower those conditions, right, I went from 73 and 46% humidity to 70 degrees and 25%, which is more of a wintertime scenario inside a building. Look how much longer the virus is going to survive, right? It went from, to get 99% of it gone, 277 minutes to 3,700 minutes. So having cooler, drier spaces is really detrimental to getting rid of COVID. You're going to want to keep your set point a little bit warmer, and you're going to want to find a way to add some humidity to your space and open up all your curtains and stuff like that if you can in the building. Now, we mentioned UV light. Let me see where I'm at time-wise. I'm doing horrible on time, as you might expect. We mentioned UV light. You can put artificial UV light into buildings. That's possible. It's usually going to be UVC light. That's the bandwidth that we typically use. UVC light is well established since the 1950s. We've been using this to clean and disinfect stuff. It breaks down the DNA of microbials, including viruses, including COVID. So we can use this to destroy COVID. Now, there are some things that make more sense than others. We're going to focus on HVAC systems because this is an HVAC subject. But you can put stuff in other spaces like in the room to try to kill stuff as well. You may have seen things like this where you can put UV light on your phone to disinfect it, or a toothbrush cleaner you can stick in at home, handheld stuff like that. But you have to hold it over the object for a fairly long amount of time, right? So if you have this handheld one like she has on the top, you would slowly pass it over the top of the desk. You wouldn't just go like that and run past it. You would go slowly past it and then move on to the next desk and the next desk and the next desk. And you can use that to disinfect stuff. The phone one, you probably have seen that if you've gone to like the Sprint store or the Apple store. They have stuff like that typically. The big thing with the UV light that you have to pay attention to is that we need a certain kill dosage for each kind of bad thing that I want to kill. The kill dosage is a function of UV source intensity. Like the sun is a giant UV source, a lot of intensity, can kill stuff pretty good. And a function of time. So for example, if I go outside for 4 hours and it's sunny out in the summer and I got no sleeves on, I might get a sunburn. But if I go outside for 5 minutes to grab my wallet out of my car because I forgot it, I'm not getting a sunburn. It's not going to kill my skin cells. I need a long time in the UV light to kill stuff. Well, every bad thing, bacteria, virus, mold, etc., has a known tested CT value, or what I'm going to call a kill dosage. It has a unit of measure of microwatt seconds per centimeter squared, and you can look this stuff up in a table. Now, the UV bulb, the further you get away from it, the less killing power it has. If I say it has 100% killing power at 1 inch, by the time I get 8 inches away, it only has 1.5% of the killing power. It lost 98.5% of the killing power. So stuff closer to the light gets killed. Stuff farther from light typically doesn't get killed unless it's there for a very, very long time because the intensity goes down, so I need longer time. We can figure out how much time we need. There's published tables like this one here that shows the microwatt second per centimeter square UV dose kill rate for various bad bacteria and molds and viruses, and I can look them up in a table. There's 2 columns, 90% reduction, meaning 10% of the bad things still survived, and 99% reduction, meaning 1% of the bad thing still has survived. So I can look those things up, and if I look a couple of them up here, I got some examples for you. Here's a bacteria that I looked up. It was 1160 to get down to 90% or get down to 10%, excuse me, I use a standard UV bulb, actually a fairly good UV bulb, 800 microwatts per centimeter squared at 1 foot rating. I need 14 and a half seconds of shine time within 1 foot. If I look at another one, influenza, flu, right? If I want to get, and flu is pretty easy to kill. If I want to get down to 1% survival rate, 99% kill rate of the flu, I need 6,600. So I need 8 seconds of shine time. When I start doing the math, like, oh, 8 seconds isn't that bad. Yeah, but here's my light bulb in my airstream, and here's the air whipping by at 500 feet per minute. 500 feet per minute is 8 feet per second. That's a lot. That's a pretty good amount of speed. You start doing the math on that, and you realize you need to bathe the duct system in 66 feet worth of light bulbs spread 2 feet apart. Holy crap, that becomes pretty unachievable. I thought I was going to buy one light bulb and stick it in there. I need 66 feet worth of light bulbs every 2 feet. That's a lot of bulbs. Here's COVID specifically. It wasn't in this other chart because it didn't exist at the time this chart was made. But I got somebody to send me some early on test data in microwatt seconds per centimeter squared. If I want to kill, say, 99.9% of the COVID in the air, meaning 0.01% survival, I need 3640. If I'm a little less conservative and I want to get 0.1 survival, I need 2730. So if I do the 2730 math, meaning I got almost all of it, I need 3.5 seconds. So I still need 28 feet worth of light bulbs spread across the duct 1 foot apart from each other, or 2 feet apart from each other, so they can all shine in 1 foot. It's unachievable. Can UV light kill COVID? Absolutely. Is it going to kill COVID in your airflow? Absolutely not. No chance. Zero. And I'm not the only one saying this. I'm doing the math on this stuff here. But here's even one of the major light bulb manufacturers, Philips, putting out their data on their kill rates, showing that they need to basically, at 500 feet per minute, standard air conditioning airflow, they need 6 seconds and 50 feet of duct to get the job done. So it's just not practical to do it this way. It's really good at cleaning coils. That's his job in life. The coil, your evaporator coil, right? So at your house, it's the coil sitting above your furnace that does all your cooling capacity. In your commercial building, it's in the air handling system or the rooftop. That coil gets dirty and nasty stuff can grow on it. UV lights are excellent at keeping coils clean because the coil doesn't move. It's there forever. So if I need to shine on it for 20 minutes, fine. It didn't go anywhere. I could shine it all day long. But shining on it, something in the air and cleaning the air that's moving, no chance. I'm going to bypass a few of these in the interest of time just to kind of keep moving, but we can help you out with data on how you would position UV lights on coils to keep coils clean. That's what they're useful for. There is benefits to that. The cleaner the coil is, the better it transfers heat, and the better I can move airflow through it. So there's a lot of benefits for it, but killing COVID is not one of those benefits. There are other technologies that I can use to try to kill COVID. There's a bunch of them. I'm going to highlight a few of them here quickly, and then a couple of them we're going to focus on when we talk about restaurants, fitness centers, and schools, because some of them are better in some applications versus others. I'm going to talk about these three simultaneous: PCO, carbon, and Oxy-4. PCO is photocatalytic oxidation. That means there is going to be a bulb in it. It's going to be a UV bulb, but his job is not to shine on something and kill it. His job is to shine on a metal cage and use that. Well, there's a UV bulb in there, and if it shines on the coil, that's helpful. But his job is to shine on carbon to regenerate the carbon to absorb odors. And his second job and primary job is to shine on a metallic cage with titanium dioxide. And when UV light shines on titanium dioxide, it creates oxidizers, hydroxyl radicals that go down the duct system. These are unstable compounds, which at first sounds scary, right? If you flash back to high school chemistry or whatever, you're like, oh, radicals, that's not good, right? It goes down the duct, these hydroxyl radicals, and then it reacts with other stuff. Everything in the universe is trying to get to a stable point. So if he's unstable, he's going to jump onto something and rip pieces of it off to become stable. So he's going to break down chemicals and things in the space and make them into more benign stuff. This is visually kind of how that looks. A UV light shines on titanium dioxide plate. It creates oxidizers. Those oxidizers can break down VOCs and things like that. Because they are charged, they will also conglomerate on some of these germ cells, and they will basically suffocate them for the carbon dioxide that they need to survive, and they'll bust them apart. It's pretty benign. There's lots of different versions of this out there, and it looks different, and sometimes it's a plate, sometimes it's a tube, but there's lots of ways that this can actually work. We also use another one called Oxy-4. It does the exact same thing, but has one more oxidizer in it. So that's why it's Oxy-4, it's a fourth oxidizer. So we'll kind of explain that as we kind of move along. But those guys can be pretty powerful. They come in multiple sizes. We size them for your application, how much airflow you have into the space and what you're doing in the space. They get mounted in the duct. It's a pretty simple installation. If you can't mount one into your duct, there are magnetic ones that can mount inside the air handling system as well. So there's lots of ways to get that done. And you can start tandeming these together. You can put two of them together to handle, say, a 20-ton rooftop unit. And you could do even bigger systems, but at some point it becomes kind of like, okay, what am I going to do? Put 15 bulbs in this giant air handler? At some point, we do it a different way. Maybe that's secure air. Maybe that's a different solution I'll tell you about in a little bit. So it's kind of scalable for 10, 15, 20-ton systems. And then we're going to probably go another path because it's not super scalable at that point. Bipolar ionization is one of those paths you might want to consider. Bipolar ionization means there's two poles, bipolar. If you look at these two needles over here, this guy is going to be charging stuff in the air and making a plasma field as the air moves across him. So these ions are present in nature. What we're going to do is artificially make them and make a ton of them. I want to make hundreds of these guys because they're going to go and break down stuff for me. They don't last very long though. Depending on whose study you look at, 60, 120 seconds, something like that is how long they're going to last. So I got to make them, get them down your duct system and into your space where they can quickly attack something. I don't want to waste any time with that. It's not new. We've had ionization for years and years and years, so it's pretty well studied. That's an old article. We're not going to have time to dive into that today. But we're charging things positive and negative. So I got those two needles. One of those needles is charging something positive. One is charging something negative, and we're trying to cause collisions later on with that. It's good for odor control as well. And any given chemical, I can look and see what its electron volt count is. And anything under 12 volts, it's going to be able to attack pretty well. Things above 12 volts, not so much, unless I do it differently. So for example, I got ammonia here. It goes to this plasma field that I created. Ammonia is a chemical you probably don't want to breathe very much of. It busts it apart into 4 different little atoms. And then they could combine together as the same thing again, but that is pretty unlikely. Chances are much higher that they'll jump onto something else. If 2 of those hydrogens jump onto an oxygen, that's H2O, water vapor. I'm good with that. If the 2 nitrogens jump onto each other, that's N2. N2 is like 80% of the air we breathe. I'm good with that. So most of these things can be broken down into more benign things, and they'll reform as a less harmful chemical. They also have the ability to cluster around stuff because they have those charges associated with them. So they can cluster around things, and in the case of something like a virus, those hydroxyls are a detergent. They clump around it and they cut it off. They remove its ability to get the carbon dioxide it needs because it's basically suffocated them. Not the carbon dioxide, excuse me, the hydrogen that it needs because it's basically suffocating them. So it will break down chemicals. It will kill bacteria. It will inactivate viruses. This is from ASHRAE as well. Here's the MERV ratings we were talking about before. And here is his chances at catching SARS virus. Now, this is the old SARS virus because this data has not been studied on CoV-2 yet. So we're using it as a kind of a surrogate for right now. Just keep that in mind. I'll show you some COVID stuff in a little bit. But this is how much he's going to catch. So if you have a MERV 8 filter, he's only catching 11%, kind of on accident, whoever kind of had that impingement collision with the filter. And you start getting up to the ASHRAE recommendation of MERV 14, which would be somewhere in the middle here, and you're going to get more than 50% of them, which is why ASHRAE, in my opinion, picked the MERV 14 recommendation. They'd love for you to put HEPA and get 99% of the COVID, but your system can't handle the HEPA filter, so they're giving you a MERV 14 like, hey, let's get at least half these guys. If I combine those high MERV filters with a UVC light, I can do even better because I'm going to kill some of that COVID that happens to make its way near the bulb, if it happens to even get back to the filtering system. Or I can combine it with an ionizer, and I'm going to get even better. So if I take a MERV 13, instead of 46, I can get 84% combined with a UVC bulb, or I can get 98.8% when I combine it with an ionizer. Because the ionizer is going to go out into the space and actively attack these things and either break them down. And if it doesn't have time to break them down, it's at least going to be clumped onto them to make them bigger and heavier. So now they will get sucked back into the filter. So my MERV 13 filter will be acting more closer to like almost a HEPA type filter. MERV 13 with an ionizer gets me damn near HEPA filtration, 98.8 instead of 99.9. So I can do a pretty good job with a low pressure drop MERV 13 combined with an ionizer. If you do a HEPA, that's great. And if you can combine a HEPA with an ionizer, awesome. You are in stud mode. You're HVAC god at that point. There are numerous studies that kind of illustrate all that. You can get a higher MERV rating when you combine needlepoint bipolar ionization with an average MERV filter. You can get pretty high MERV ratings. There's a couple different studies out there. In addition to this one, there's a couple other studies out there showing the same kind of result. We use one from a company called GPS, Global Plasma Solutions. They have all kinds of different ones that they make. We don't have time to dive into all of them. There's a couple we'll look at for some specific applications and some of the other topics coming up. But they make all kinds of different ones that fit in air handlers, residential, commercial, ductless mini splits. There's a wide variety of options, and we'll talk about some of those as it relates to the applications we look at in a little bit. All right, so we'll dive into those. Big air handlers as well you can do. The interesting thing for them is that they are the first manufacturer to have some test data this summer showing 99.4% deactivation of SARS-CoV-2 specifically in 30 minutes. So in 30 minutes, they were able to knock down 99.4% of the SARS-CoV-2 virus. This is back in June. There's a little bit newer data now where it's like 99.9%, but statistically that's still the same thing in my mind. So first and possibly still the only one to have SARS-CoV-2 data. There are other manufacturers of things, including things that we do at our office, that have literature published out there showing their kill rates on coronavirus, which is fantastic. But when you read it, it's coronavirus, meaning one of the other coronaviruses, not specifically SARS-CoV-2. So this is the only one that has SARS-CoV-2 data thus far. And they have data for all kinds of other bad stuff too, and they have all that stuff published showing their inactivation rates on stuff. COVID-19, SARS-CoV-2, is fairly easy to get rid of if you use the right technology. It's certainly easier to get rid of some of these other ones. Actually, it's the easiest one on this list to knock out. The thing that comes up sometimes is some of the things you put in your system might create ozone in their attempt to kill stuff. Ozone is a very potent oxidizer, and it'll kill lots of germs, which is fantastic. And some applications will do that. And other times we'll say, you know what, I don't want to create a bunch of ozone just for the sake of creating ozone. And some customers may want to have no ozone emissions. That might be a goal of theirs. The nice thing about this technology, needlepoint bipolar ionization, is the ones that we use are at 12 electron volts, and oxygen is at 12.07. Oxygen, O2, when I run it through an ionizer, would become O3, which would be ozone. Well, this guy doesn't work on anything above 12, so he's not touching oxygen, so he's not creating any ozone. It is one of, I believe, 2, maybe 3 manufacturers that have gone through the UL testing process for 0 ozone emissions on air purifiers. It's a very short list of manufacturers. They're definitely the only one that does COVID and has 0 ozone emissions. So we've been using those a lot. They get used a lot in hospitals. The White House has it. I don't know if this isn't a political thing, so maybe you don't care about the White House, but it's obviously somebody who's trying to keep things minimal. A lot of universities are doing it, which is a pretty good endorsement of a technology. If they're putting it in their own buildings, pretty good chance. The Google headquarters, both locations, both Google buildings, the offices have these guys in there. They have an older style one, but nonetheless, they've had it in there for years. Last thing I'm going to leave you with, because we're running out of time, and we have more topics coming up for you, is you want to find some tools that you can use to measure some of the things in the air. This is one that I have. I have it mainly because it's not super expensive. It's only hundreds of dollars instead of like tens of thousands of dollars for high-end stuff. But I can take it around, set it up, and in a short amount of time, I can get some basic data like particulate measurement data, carbon dioxide in the air, VOCs in the air, my usual favorites of temperature and humidity. I can get some pretty quick data. There's lots of tools like this. I just like this one because it's inexpensive and it goes to an app on my phone and I can save the reports and stuff like that. We have tons of other ones we use. We have handheld particle counters and we have handheld CO2 meters and we have building automation systems to track stuff. It can get pretty elaborate, but you probably want to find something and let me know if you don't have something that you can use to start tracking some of the things in your building and what you can do with it. All right, let me see what other questions might have gotten generated. This is a quiet group thus far. And literally nobody sent any questions in. You're making me so sad. I'm going to stay on here for a little bit, like maybe 3 or 4 minutes and see what else comes up. And in the meantime, I'm going to put this back up for you. So these were the other topics coming up. So tomorrow morning, if you run a restaurant business or you work with customers that run restaurants, take a look at this. We're going to give you some application things to make your air quality better, both in general and related to COVID, to make a better chance of you opening your building. Then in the afternoon, we're going to do the same thing for sporting venues, meaning specific, not like an arena, not that kind of thing, although it would work, but more like fitness centers, gyms, MMA clubs, karate studios, that kind of stuff, those kind of buildings. We'll talk about Friday morning, we'll do schools. And then Friday afternoon, we'll do home solutions if you want to do something at your house to make your air quality improved. All right, let me see what other questions. Did anybody type anything in? Got a couple thank yous. Okay, here's one from Jeff. I need to make the window bigger to read it. Did I see hydrogen peroxide solution? How does this compare to GPS? I didn't mention anything about hydrogen peroxide. A couple things with hydrogen peroxide. You can obviously get the brown bottle stuff. You pour it on a cut. It disinfects the cut. You can do that. There are technologies that create a aerosol version of hydrogen peroxide. I had one of those at my house for about 6 years. I thought it was great. It did a great job. But I moved on to other technologies now, and they're also doing a good job. But you can do that. There are things that will do that. Thomas asked if we have a expense breakdown per ton or PFM. I'm not sure what PFM is, or CFM he probably meant, for different application that can be referenced as a rule of thumb. I don't have any good data on costs, primarily, and we may have it at our office, I don't know, primarily because I don't get involved in sales in any way whatsoever. That is both my flaw and my gift. I just get to explain how things work to people. I literally teach all day long, explain how things work, and then at some point in time, somebody gets a quote from somebody else in my office to do stuff. So Thomas, we can probably find that out for you. It's going to be different depending on which technology you want to use, filters, UV lights, Oxy-4s, GPS, whatever it is, what technology you want to use, and what kind of equipment you have at your building to get it to fit in there physically, because that changes a lot of the discussion as well. We're going to go into some of that stuff and the other topics. But if you have a specific one that you want to look at, like, hey, I got this air handler at this building that's this much CFM and I have this much space to work with, I can get someone in my office to generate you a quote and tell you what that's going to cost. Rob said he's only doing the audio, not the slides he can't see. He's only doing audio and want to know what is used at the White House. Global Plasma Solutions has installations at the White House, which is a bipolar ionizer. I'll give it a couple more minutes to see if anybody else pops anything up. Okay, I don't see anything coming up, so either you guys are all satisfied or you're really slow typers, one or the other. But you can always contact me later. I will put my info back up. If you got a question you want to send me, there's my email. Feel free to send me something and I'll try to get it answered. I teach during the day, so you'll probably get an answer at night. So I apologize for that. But Jeff says, trying to figure out what filters to use for restricted airflow. So while I'm answering, Jeff, type something in and let me know. Oh, for not restricting airflow. Type something in and let me know what kind of system you're talking about, what kind of equipment it is, and I can probably give you a better answer. But right off the bat, for filtration purposes, one of the best things to do is that MicroClean 95 I was talking about. Well, where's it at now? If I have a lot of space to work with, I can use secure air. Like if it's an air handler, like at a school or something like that. If it's more like a rooftop unit, like at a restaurant, then I'm going to be space constrained as well as airflow constrained. Okay, Jeff says 45 residential units. Okay, so you're not putting in something like this. Secure air, like we use this a lot for hospitals, they do actually make a residential product. It's like, I want to say 7 or 8 inch wide cabinet with like a 4-inch filter in it. And you may be able to do that. I have a very similar one. Mine's called the Carrier Infinity. Very similar to Secure Air. Some of the same engineers worked at both companies. I have that at my house and I love it. But 45 units you're looking at, you're probably thinking of something that's going to not be as much space taking up. It's probably a condo building, something like that. So you're probably going to look at something like this. There's a 1-inch and 2-inch version. You're probably going to go more towards the 1-inch version on top, Jeff, because you don't have a lot of space to work with. And the nice thing is you can order this in different dimensions. So let's say all your residential units, or a bunch of them anyway, have 20 by 25 filter racks on them. I can order these MicroClean 95s in a 20 by 25 dimension, slide it into the existing 1-inch slot that you already have, and then all I have after that is a 24-volt transformer that plugs into an outlet that moves over and connects in right there. So it's all easy to install. It fits in your existing rack. All you have to do is have an outlet somewhere nearby to plug it into. And you probably already have an outlet. Most residential units and furnaces have an outlet next to them anyway. If not, there's probably a way you can just, actually you could probably tap it into the 24-volt transformer off the furnace or the fan coil. You could do that too even, and not even need an outlet to plug it into. You can get it done either way. That's probably your best bet for 45 small residential units. James says MicroClean 65 or UltraClean 99. I'm assuming he means MicroClean 95 or UltraClean 99. So MicroClean 95 is what I'm showing here. And this is very scalable to commercial equipment. The UltraClean 99 is a beefed up version of that, if you will, but it's a wider cabinet again. So it's more like that Secure Air one I was talking about. It's a wider cabinet. It has an ionizer built in like this does. So on a residential furnace at your house, that's definitely a viable solution. Sticking it into commercial equipment, it's not going to work. Plus it has its own dedicated rack. So really it's only a one module thing that I could put on a small system. Whereas this, I could get 6 of these and slide them into an existing rooftop rack if I wanted to. So if you're talking about residential, that would make sense. James says he does a lot of RespiCare stuff, so you probably know some of these things we're already talking about. What else? I know we went over our time, but if anybody has more questions, I'll hang out as long as you guys keep having questions, I suppose. For you guys that have asked some of the residential stuff, definitely tune in Friday afternoon because we're going to focus on a lot of that stuff, specifically residential stuff. All right, I am going to log off and compile this video recording so I can post it for people that missed it. Thank you guys for your time, and hopefully I will see you, or you'll see me tomorrow morning. Thanks.